and I'm going to simulate topological Kleene field theories. This means that I'm going to construct some dynamics that are capable of computing. So my talk is going to be about topological Kleene field theories that are a new framework in the world of computational theory, where computations are introduced as flows in bordisms. This was introduced by González Prieto, Miranda, and Peralta Salas, and I, in the summer school organized by Wolfram in 2025, mentored by Duan Hamo, I translated this abstract construction into concrete terms, explicitly computing these smooth dynamics. So how is going to be the outline of my talk? First, I'm going to talk a bit about these ideas, introduce them, and then talk about the goals of my project. Then I'm going to actually talk about what computation means, what are Turing machines, and how can we see these computations as dynamics in the counter set. Then we are going to talk about actually what are topological Kleene field theories and how can we understand them. And then we are going to simulate a simple Turing machine that is going to be very simple, and we are going to be able to understand this construction with it. And then we are going to see some recent work that I have developed that let us introduce these computations in any way, like any Turing machine that can be simulated using these techniques. So let's start. So first of all, what does it mean to compute? So in some sense, computing is transforming an input into an output. So our goal will be to construct a flow that does this. So our flow is going to be in a cobordism, some type of tube or pipe. So there is going to be an initial disk and then a final disk. So our input is going to be a point in the initial disk. And this point is going to be driven by the flow that we are going to have in this bordism, in this manifold, and it's going to hit another point in the final disk. So if you give me any computation, for example, imagine that you construct a program that squares a number. So there is going to be some pipe, some construction, some manifold that is going to square a number. So how does it going to work? We are going to have here a point that is going to represent, for example, 7. We are going to let it flow through the vector field that we're going to have in our manifold, and it's going to hit the point that represents 49. But at the same time, if I have here the point that represents 3, I'm able to let it flow here, and it's going to hit another point that represents 9. That way, if you give me any computations, I can construct a manifold with a vector field that simulate that computation. Okay, so how are we going to do this? We're going to use topological Kleene field theories that, as I mentioned, were introduced by González Prieto, Miranda, and Peralta Salas in 2025, and allow us to reinterpret this computation by means of flow on a smooth bordism. But actually, why do we care about this? So why do we care about computing with dynamics? So there are two sides of the same coins, and the first of it is because of dynamical reasons. Basically, if we can show that some problems in dynamics can be understood as some problem in computation, we can see, for example, that some problems in dynamics become undecidable because of the halting problem. It's equivalent to answer those questions in dynamics as it is to answer those questions related to the halting problem. So there are some problems in dynamics that are undecidable. Also, if we know that the dynamics are complex enough to embed computation into that, we can kind of get some more information about solutions to differential equations. For example, Terence Tao suggested a few years ago that maybe it's possible to embed computations into Navier-Stokes. And this way we can study these very, very difficult equations using the computation that we get as part of the flow. The other side is the computational side. So maybe trying to embed these computations into dynamics, it's a very good way to understand more things about computation. For example, we can try to relate the computational complexity of the function that we are computing with the topological complexity of the bordism that we get in this way. And also, there is some potential to provide a new way of computing that might be even faster than certain computation that we have right now. So let's go. Let's start working. So how can we do this? What is a topological Kleene field theory and how does it work? So the first thing that we need to understand is how a Turing machine works. So we need to ask Alan Turing, what does it mean to compute? How can we define computation? So that's why Turing machines come into play. So basically, a Turing machine is a tape. So each step of the Turing machine consists on a one-dimensional tape. So for example, here we have one-dimensional tape. So each of these rows is one step of the Turing machine, and a head that here is represented with an arrow. So the arrow can have several states. For example, this one here has two states, a state up and a state down, a state 1 and a state 2. So depending on the state of the Turing machine, of the head of the Turing machine does one thing or the other. So for example, here, if we are in state 1, pointing up, and then we read in our tape a 0, which is represented here by a white square, we know that we have to change this 0 by a 1 that we represent here with a blue square, and then move to the right and change to state 2. For example, here, if this is exactly what we do. We change this 0 where the head is into a 1, and then we move right and we change to state 2. And then now we are in state 2, we read a 0, so we come here and say, okay, these are my results of the Turing machine. So you know that if I read a 0, being in state 2, I need to change that 0 by a 1 and then move right, and then we can continue the computation until it ends, or maybe it doesn't. So that's actually the halting problem. So this whole idea of the Turing machine is very powerful, because actually any computations can be represented by a Turing machine, because itself, the Turing machine is the very definition of computation. So there is a definition of computation, and it's basically whatever a Turing machine can do is what a computer can do. So our idea is to simulate this Turing machine, to translate this Turing machine into the world of dynamics. So there are two important things here. So basically, yes, this is the idea, to translate Turing machine into bordisms so we can compute using bordism. So there are two things that we need to encode into the dynamics: the tape and the head state. So basically, what is the collection of zeros and ones that we are working with? And secondly, if the head, the current state is in state 1, 2, 3, or depends on how many states we have. So this way, if we have a concrete Turing machine, we can get a manifold with some flow on it that we can use to compute. Okay, so first step, encoding the tape. I'm going to check. By the way, if you have any question, please feel free to ask me at any moment. I'm going to be checking the Q&A section. So first thing that we need to encode the tape of the Turing machine. So basically, the tape of the Turing machine, we can see it as two lists of zeros and one. How? Basically, the head of the Turing machine is going to be in a certain position. So we can look at all the points, all the tape, the position in the tape that are on the right-hand side of the head state, including the head state. For example, here, these, so all the ones that are here. So we can see it as 0, 0, 1, 0, 0, 1, and so on. And then we can see another list, which are the remaining spaces of the tape. So all the ones that are to the left of the head. So in this case, 1, 0, 0, 1, blah, blah, blah. So for example, if we change to another state, we change from being these two lists, from having these two lists to having these two. Because now you see that if I move from here to here, now my right-hand side is going to be 0, 1, 1, 0, 0, 1. And here it's going to have 1, 1, 0, 0, 1. So all the thing that we have here. So basically, the idea is that a Turing machine, what it is actually doing is transforming these two lists of zeros and 1. So what are we going to do with two lists? So we are going to encode these two lists as points in a two-dimensional Cantor set, okay? So let's recall quickly how the Cantor set is actually constructed. So we know that the Cantor set is constructed inductively. So we can use this animation that was produced by Robert Grease. So basically the idea is that the Cantor set is a set in the unit interval that we create by dropping middle thirds. Iterative, it's an iterative process, and if we start dropping the middle thirds of what we have remaining, we get, after doing this an infinite amount of time, we get the Cantor set. But about what we actually care, the important definition of the Cantor set, and it's equivalent to the one we just defined, is that the Cantor set are those points in the unit interval whose ternary expansion, and I mean the expansion in base 3, if we write them using base 3, only uses zeros and 2. Exactly the points that we were dropping before, the middle thirds, are those points that contain at least a digit 1 in the base 3 expansion. So if we have a point in the Cantor set, we're going to have a number that only has zeros and 2s. So what are we going to do? We're going to take our infinite list of zeros and 1 that we got from the tape of the Turing machine to we are going to multiply it by 2. So we have our zeros and 1, and then we change it to zeros and 2, and those are going to be the coordinates in the point in the Cantor set. So as we had two lists, one corresponding to the right-hand side of the tape and the other to the left-hand side, we are going to get two coordinates. One is going to be our horizontal coordinate and the other the vertical coordinate. So we can see some example of how we can do this. So for example, if we have here this tape, we can see that the right part is going to be 0, 0, 1, 0, 0, 1. So we multiply by 2, and these are going to be the coordinates in my x direction, the horizontal direction. While the left tape here is going to be 1, 0, 0, 1, and we can use it as the coordinates of our vertical direction, our z direction. So Each point, we can associate each tape to a point in the Cantor set and vice versa. Each point in the Cantor set, we can interpret it as a tape of a Turing machine. So basically, what is this telling us? It's telling us that the computations, the Turing machine that was changing the tape of the Turing machine that was transforming this tape of zeros and one is equivalent to dynamics in the Cantor set. We know that the tapes are equivalent to points in the Cantor set. So now we know that changing those tapes is equivalent to moving around the Cantor set. And we can actually see how a very difficult Turing machine, a very complex Turing machine, is just basically moving around the whole Cantor set. So now we have already translated these computations into dynamics, discrete dynamics, but into dynamics. So now let's see, what can we do now? The title of my talk actually was not the computation through a discrete dynamic, it was through a smooth dynamics. So we're going to transform these discrete dynamics into a smooth dynamics. And how are we going to do this? We're going to construct some flows that implement the two possible actions that a Turing machine can do. Basically, a Turing machine can rewrite a symbol or shift the tape, moving around. So we are going to construct some flows that, if we apply them to all the points in the Cantor set at the same time, we get the same thing that we will have in a Turing machine. So let's see some concrete example to see actually what's happening here. So imagine, for example, that I'm changing a 0 to a 1. First of all, my head is only changing the points where it's sitting. So we know that the first digit, as we are changing a 0 to a 1, has to be a 0. So as the 0 is the first digit in the ternary expansion of our horizontal coordinate, we know that these points are these, the ones that are on the left part of the Cantor set. And we are going to change a 0 to a 1. So it's basically changing this first digit, instead of being a 0, it's going to be a 1. So we are going to move all these points here from the left to the right. It's basically the same as having 2/3 to the x coordinate. So we can implement it as a smooth flow between two Cantor sets. Okay, so now let's think about the other one. The other movement is not changing a symbol by another, but shifting the tape. And this is actually a bit more complicated, because what we need to do here is, let's see, for example, this case. Imagine that we are shifting from here to the left. What happens to the tape? So the right tape is changing from being this one to this being this one. We have added here a 0. While this 0 was coming from the left tape, but now, since we are here, this 0 is no longer in the left tape. So basically, this point here, this position in the head, in the tape, is changing from being on the left to being on the right. So what's happening actually with our coordinates? So here, basically, we are shifting everything to the right. So if we are in base 3 and we are shifting all the digits to the right, that's the same as dividing by 3. And the same way here, if we are in base 3 and we are shifting everything to the left, it's the same as multiplying by 3. The other case, that it's a bit more complicated, is when we are shifting the head to a position that has a 1. Then instead of moving a 0 around, we are moving a 1. And here it's a bit more involved, but actually you can see by yourself that we have, again, if you compute it with the definition we have that these are, again, linear maps. So in this case, shifting the tape is, again, a linear map, a piecewise linear map that we can introduce as some flow. A bit disclaimer here, these flows are only defined on the thirds that correspond to Cantor set. They can actually be extended, and it's shown in the paper by González, Prieto, Miranda, and Peralta Salas, that they can be extended to the whole square. But we don't really care about that, because there are no computations going on these parts that they are not defined here. So in my project, we only define it on these thirds that it's enough to simulate the computation. Okay, so this is shifting the tape to the right, shifting the tape to the left is more or less the same. Okay, so now we already have the tape that we're working with, the tape of the Turing machine, encoded. So now, next step, we need to encode also the head state. So what is the state of the head of the Turing machine? Remember that little arrow that was pointing up, down? So how are we going to do this? We are going to use the graph representation of a Turing machine. Basically, a Turing machine is all the time changing from one state to the other. So basically, we can understand this as a graph, as an oriented graph. For example, here, we have an initial state and a halting state. We don't really care about those too much, but basically, we need to focus on Q1 and Q2, state 1 and 2. State 1 is pointing upwards. So we can see here that if we are in state 1, so we are here, and we see a 0 that is represented here by this 0, we need to move to the right, write a 1, and then move to state 2. So what are we doing here? We are reading a 0, we are writing a 1, and then we are moving to the right. That's why we are writing a 1. And then we are changing to state 2. Now, if we are in state 2, depending on what we have, we come back to state 1, or we halt. This is the halting condition. So basically, we can understand all the possible transition between states of a Turing machine as a graph. So what's the brilliant idea behind TKFTs? We know how to translate graphs, the head state as graph, and we know how to translate the tape of the Turing machine as point in the counter set. How can we combine this? So the idea is, okay, let's thicken the graph, creating these pipes. We are transforming each edge into a pipe, a tube. And what we're going to do is, okay, each of the nodes on my graph is going to represent an state. And what I'm going to do to encode the tape at that current state, I'm going to introduce a square counter set in the position of the states. This way, I have enough room to encode both the head state that is going to be represented by where I am in the graph and the position of in the tape that is going to be represented by where I hit in this counter set that are going to be transversal, that are going to be placed here on the nodes. Okay, so now that we kind of understand the topological Kleene field theories, although we are going to see an example that it's going to be much clearer, why do we care? Why this? What are the properties of this construction? So first of all, this construction relies heavily on the topology in our manifold. Look at this. When we are thickening the graph, we are getting some holes. And actually, we can see that the topology of our manifold is very, very much related with the topology of the graph. So the idea here is that we need that topology, that complexity in the topology, to be able to reproduce the dynamics. Because basically what is happening here is that depending of if I read a 0 or a 1, I'm going one way or the other. So here it's very important to have this topology. We cannot have a manifold without holes, basically. So, and actually there is some potential to relate this topological complexity with the complexity of a Turing machine, because the more complex the Turing machine is, the more complex the graph is going to be, and the more complex the topology we're getting is going to be. And secondly, the flow is generated by a small vector field. What does it mean? That trajectories do not cross, okay? So in real terms, it means that we can only simulate reversible Turing machine. And this is actually kind of important to construct this, to prove that this can be done, but not so important in practice, because it is proven in the paper by González Prieto, Miranda, and Peralta Salas, that if you give me any Turing machine, I can increase the number of states and I can get a reversible Turing machine. Okay, so now let's get to do what we all came here for. We are going to simulate a TKFT. So what are we going to do here? So we are going to take this very simple two-state Turing machine. We have here, so these are the rules, and these are the states, the graph representing the Turing machine. And we are going to thicken this graph. And we are going to create the dynamics that emulate this Turing machine. And what do we get? We get this. So let me run a bit through a computation and see what is happening here. So basically, this thing here is equivalent to the graph. Okay, look at this. So this graph here, if we thicken it, we get something like this. So what are the states on the Turing machine? This is the initial state where we start. We don't really care about that. This one here is state 1. This one here is state 2. And this one is the halting state. So basically, this line that we have here with all the states, this straight line, is this straight line that we have here. Okay, so let's begin the computation. So we begin the computation, and I'm going to go a bit slower. So basically what's happening here is that I'm hitting the first, so look at this trajectory, what's happening? I start here at the state 1. So the first thing that I hit is this square that represents state 1. And what am I reading with the Turing machine? I'm reading a 0. So how can I see that the Turing machine is reading a 0? A 0 is represented by the left part of the counter set that we have said earlier, because that 0 is the first digit of the horizontal coordinate. So it's a 0, so we're in the first third. So basically, why do the Turing machine knows that we're hitting here a 0? Because it's hitting this square on the left part. And then what is the transition the Turing machine is doing? It's changing from state 1 to state 2, moving to the right, and then writing here a 1. So there are 3 things that we need to do. First, we change the 0 to a 1. So we go from the left part to the right part. Check. Then, next thing we need to do, we need to change from this position to the right position. This is done here. So basically, in all these sections, we have the flows that I showed earlier. And finally, we need to change from state 1 to state 2. So where is state 2? Here. Remember, state 2 is here. So we are moving to the square in state 2. So basically, we are changing from here to here. We are doing this change in the graph, and at the same time, we're encoding the information of the tape in the square Cantor set. Okay, so next, what is happening here now? So what is happening is that I'm moving, so I'm in state 2, and I read a 0. So I was here, remember, and I'm reading a 0 because I hit the left part of the square, and then I'm coming back to state 1, but in the process, I'm changing the 0 to a 1 here. I'm moving the head 1 position right, and then I'm going to the 1. And look at this now. So basically what I did was going through this edge. Now look at this now. Now I'm hitting state 1 in the right part of the square. Why? Because I'm reading a 1. So now that I'm reading a 1, I'm not using this transition. I'm using this one, the one on the right. So what I'm doing here, I'm going through this right part of the donut. So what I'm doing is, okay, I have here a 1, I change it to a 0, then I move the head to the right, and then I come back to state 2. So basically, I can run the simulation until the halting condition is met, and then we exit through the last square. So basically, this is what topological Kleene field theories are about. Okay, you give me a Turing machine, and I need to translate two things: the head, the state, and the Cantor, and the tape that is encoded in the Cantor set. So the head state is going to be encoded on where I am in my manifold. If I'm here, 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 here. So if I look from above and I see where the point is, it's going to tell me what the state of the head is. And then if I look transversally and I look at the position on the square, it's going to tell me what my current tape is. Okay, so now that we have this, you can tell me, okay, but this is very simple. This is a really small Turing machine. It's kind of useless. So yeah, so but one thing important here to be remarked is that this construction, it's valid for all possible inputs. So it means that this Turing machine, any input, the Turing machine is represented by the same flow. So depending on my initial condition, I have different input for my Turing machine, and I can see the different trajectories. For example, here, this one in red halts very quickly. So it only goes through here and then here. While the one in black halts very much later. So it goes around many times until it hits the final disk. So yeah, but let's do something more interesting, and let's simulate any Turing machine. And this is actually one of the recent development I've been working with. So the idea is to create a simulation, some function that is capable of simulating any Turing machine. And how are we going to do this? And this is actually a bit difficult. Why? Because before I knew that I had this graph. So I could thicken it, and I could compute the flow of this graph explicitly for this graph. But now the problem is that if you give me any rules of a Turing machine, each Turing machine is going to have a graph. And the more states the Turing machine has, the more complex is going to be that graph. So I need to figure out a way to lay out this graph, so when we thicken it and we get some pipes, they don't collide with each other, because we need to have something smooth, something that doesn't collide. So what is the solution to this? We are going to create some adaptable pipe system. So how are we going to work? So basically the idea is, okay, give me a Turing machine with n states. For example, this one has 3 states. So each of these states is going to be represented by a square in a line. Okay, so they are going to be all in a row. And what's the idea here? That if I want to travel from one state to the other, I'm going to travel in a certain height, at a certain level. So all the pipes, for example, that are leaving from state 1 are going to travel at height +1 or -1. This way, they are not going to collide. You can see here that this pipe is traveling from state 1 to state 3 through height 1. So it's not colliding with anything. While here, for example, the pipe that is leaving from state 2 is traveling at height 2. You can see here. So it has some space to move around, to go wherever it needs to. For example, here, this state 2 is coming back to state 2. So it goes through here, and then it comes back to state 2. And there is no collision, because the pipes that are leaving from state 1 travel at level 1 and -1. The pipes that are leaving from state 2 travel at level 2 and -2. And the pipes that leave from state 3 travel at level 3 and -3. So there are no collisions. And we can generalize this to any number of states we want. For example, if we have 6 states, it's kind of crazy. Now we are talking business, like we are talking about real important Turing machines that can actually be useful to compute something. So here we have many, many different states. You can see state 1, 2, 3, 4, 5, 6. And the farther away I'm going, the pipes are traveling higher and higher and higher. But I don't have any problem because you can see here, all the pipes are at different levels, so they can travel around wherever they need to, and there are no collisions. So with this, we can actually show that these computations, TKFTs, are shown in the paper, the original paper, are Turing completeness, and that any Turing machine that you give me can be simulated with this. So we can change both the input of the Turing machine, but also the rules, and you can construct anything simulation with anything you want. For example, the Turing machine we just saw, we can plug the rules here, plug some input, and get a simulation on how this works. So basically, if you give me any reversible Turing machine, but remember that if you have any Turing machine, your favorite Turing machine, you can transform it into a reversible Turing machine by adding some more states. I can give you a simulation that computes this. So this is basically everything I wanted to talk about. So yeah, so basically, these are the first concrete steps to realize TKFT as a framework for computing through smooth dynamics. And this suggests a really promising research direction and intersection of dynamical system, category theory, and theoretical computer science. So for further work, it's very important to further understand and visualize the structure of the vector fields associated with these flows. We should also try to analyze the dynamics for points outside the Cantor set and explore if they can be used to improve this computation. And finally, explore some ideas on how to embed computations into other continuous dynamical systems. So that's all. I want to acknowledge my mentor at the Wolfram Summer School, Dugan Hammock, also the original authors of the paper, González Prieto Miranda and Peralta Salas, and of course, Stephen Wolfram for his very valuable suggestion. So this is all. So I just recommend you to come and visit my first post on the Wolfram community post that I did just after Wolfram Summer School, where I explain the very basics of these computations, and my new post, recently uploaded, where I show how these smooth dynamics are Turing completeness. So that's all. Thank you all for coming. And please, if you have any question, let me know. So, okay, so I have here a question by Sabrina Perez Watts. So what inspired your approach to solving this problem using Wolfram? Okay, so let me display it. I think it's now displayed. So basically, what inspired me to use Wolfram here? So first of all, I think this is pretty much related with the work of Stephen Wolfram himself. So, and he had really valuable insights about how to carry on this project, because he has thought a lot about what computations mean and how can we compute using a continuous dynamical system. So that's definitely a really important thing. And I was actually already familiar with Wolfram language. So I have used it before for some simulation, and I think it's amazing because, first of all, the very Turing machine function that I use to represent the Turing machines are already implemented in Wolfram language. So it's a very, very easy way and very practical way to talk about all these things and to express all these ideas, because there are so many things that are already built in Wolfram language that you can use. So yeah, mainly, for example, the Turing machines that maybe are not that known, that you can use to actually simulate Turing machines, like the tapes I showed you using Wolfram language. And I advise everyone to come and explore it, because it's very fun to try different Turing machines and see the outputs of different Turing machines. So yeah. So any further questions? So if not, as I think I'm just running out of time, thanks again, everyone, for coming here and listening to my talk. And of course, thanks again to the organizers for inviting me to this amazing conference. So yeah, please check out my post and you can see the details. And of course, if you have any doubts, please feel free to write me an email and we can chat a bit about this amazing construction. So see you.